हाँ, so we are live. Okay, so मैं कह रहा था कि today we'll see some systems in MATLAB and also we'll discuss if anyone of you has any issues in or questions or queries in the previous labs. क्योंकि हमने जो इस बार attempt किया lab को online करने का, this was first time क्योंकि lab online करवाना it's not an easy thing क्योंकि उसमें lab में क्या रहता है कि इसमें experiments करने पड़ते हैं और it was not easy to go live for a lab. Then we decided to record the lectures और रिकॉर्डेड लेक्चर्स हम आपको दें ताकि मैं जब रिकॉर्डिंग करते थे तो उसमें कहीं कहीं पे फॉर्मूलाज या फिगर्स या टेबल जैसा मैं देखा होगा वीडियोस में मैं डालता था ताकि आपको समझ में आए कि हम लैब में कर क्या रहे थे। अगर हम वहाँ पे लैब लाइव करते तो उसमें काफी डिफिकल्टीज काफी प्रॉब्लम्स होती और वो इट वाज नॉट पॉसिबल टू सबमिट अप इन 2 आवर्स, तो 3-4 घंटे का बन जाता। दैट्स व्हाई वी रेस्ट्रिक्टेड इट टू अ रिकॉर्डेड सेशन और वो ऑलरेडी अवेलेबल है। ओके, मुझे पहले बताओ आप का डेट शीट आया है फॉर एग्जाम्स?
लैब एग्जाम्स की डेट शीट आई है।
ओके, क्या डेट है? हाँ, डेट्स आपको पता चल गए?
सर कंट्रोल सिस्टम 1 दिसंबर को है।
ओके, लैब।
यस सर।
श्योर, ठीक है। तो जो हमारा इस लैब का एग्जाम रहेगा, वी विल इट्स नॉट पॉसिबल टू डू इट प्रैक्टिकली, सो व्हाट वी विल डू इज वी विल जस्ट हैव अ वाइवा फॉर ईच वन ऑफ यू। और जो आपने रिपोर्ट सबमिट की है ना इन जीसीआर, so some marks will be dedicated to the reports already submitted and some part will be dedicated for the viva. ठीक है, तो हम आपको बिफोर 2-3 डेज इन्फॉर्म कर देंगे कि वाइवा कैसा रहेगा, उसमें क्या चीजें रहेंगी, बट मोस्टली इट विल बी ऑन वाइवा। ठीक है, सो टुडे I will start with some MATLAB. I will suggest कि जिन-जिन के पास एक्सेस है लैपटॉप्स एंड MATLAB इंस्टॉल, I will suggest कि आप ओपन करो। तो we will today क्या काम करेंगे, हम कुछ कोड अप करेंगे and we will follow. ठीक है, आप भी लिखो and I will also tell you what to write. और जिनके पास MATLAB अभी तक नहीं है या जिनके पास इंस्टॉलेशन कुछ अदर्स हैं, they can mail to me और WhatsApp कर सकते हैं, so I can just guide them, you know, how to install. या जिनके पास कुछ फैसिलिटी नहीं है, then they can just see the video और वहां से वो देख सकते हैं कि क्या करें। ठीक है, so I will start sharing my screen now. Just give me a second. ओके, सो आप लोगों को स्क्रीन दिख रहा है?
यस सर।
हाँ, आप लोगों को मैटलैब की विंडो दिख रही है सबको?
यस।
हाँ, टुडे इट्स मोर ऑफ एन इंटरैक्टिव सेशन। इट्स नॉट लाइक जैसे आप क्लास में बैठते हो और लेक्चर देखते हो, क्योंकि यहाँ पे क्या होने वाला है, टुडे विल बी कोडिंग ऑफ थिंग्स, सो इट हैज टू बी, यू नो, आपकी साइड से भी रिस्पांस आना चाहिए और आई विल आल्सो प्रोवाइड सम रिस्पांस। ठीक है, तो जहाँ पे कहीं पे भी कोई डाउट होगा, कंफ्यूजन होगा, जस्ट आस्क मी, क्योंकि टुडे इज द लास्ट लैब, सम कंक्लूडिंग दिस लैब सेशन, टुडे इज द लास्ट लेसन। तो कोई भी डाउट है जो हम आज करेंगे, हम एक काम करते हैं, पहले I will just use MATLAB and see how you simulate systems. Okay, once we are done with MATLAB, at the end we'll dedicate some half an hour or 15-20 minutes for any questions on previous जो हमने assignments किए या previous experiments किए, वो हम लास्ट में देखेंगे। We will start with basically the MATLAB. अच्छा, before we start with MATLAB, I want to know कि आपने अभी तक MATLAB में क्या किया, आपका जो है ना दूसरा कोर्स, उसमें अभी तक आपने क्या क्या किया, क्या सीखा आपने अभी तक? Anyone? Are you comfortable enough with MATLAB now?
सर एक्चुअली सर 2 सर पढ़ाते हैं, एक
क्या?
ने सर कुछ कोडिंग पार्ट टाइप का कराया और एक ने थोड़ा सर्किट डायग्राम समथिंग करके सिखाया।
ओके, सर्किट डायग्राम्स नहीं, आई एम आस्किंग बेसिकली MATLAB में अभी तक आपने कौन कौन सी चीज देखी? आर यू कंफर्टेबल इनफ टू यूज अ MATLAB? मतलब आपको MATLAB में जो जैसे मैं फॉर एग्जांपल दिखाऊं यहाँ पे, इफ यू कैन सी ऑन द स्क्रीन, आई एम हैविंग सम विंडोज हियर। आर यू फेमिलियर इनफ विद कमांड विंडो, स्क्रिप्ट्स एंड सेविंग फाइल्स, रनिंग फाइल्स, ये सब चीजें आपको पता है ऑलरेडी?
यस सर।
ओके, गुड। So I will start with a new script. Okay, मैं एक नई script ले लेता हूँ. I'm just dividing my screen into two parts. First, the upper half is a script in which I will just write my code, and on the lower you're seeing a command window जहाँ पे हम you can run some command quickly and see the results. So I will be doing that. Okay. So आज जो lab basically हम करने वाले हैं या जो हम code लिखने वाले हैं, for that you need to have some prerequisites. I don't know कि आपने वो prerequisites cover किए हैं कि नहीं. Still I will just go through them. The first prerequisite is to make the transfer function first. क्योंकि कोई भी system when you go to simulate governing equations, isn't it? And governing equations can be in the form of differential equations or can be in the form of transfer function. Okay. So what I will do is I will just write a comment here that I will create a transfer function. Transfer functions आपने बनाया है इससे पहले कभी?
No, sir.
Okay, you have not done transfer function. Okay, we will start. We'll give 5-10 minutes for just transfer function. How do you create transfer functions? And once you have a transfer function, what you can do in MATLAB. Okay. So there are a couple of ways to create a transfer function in MATLAB. Okay. I will show you one of them, the methods. Let's suppose I want to create this transfer function. I'm just writing in comment first. This green, by the way, this green line denotes a comment. So when I run this, these green lines won't run. Okay. Let's suppose I want to make this transfer function. Yeah. It's basically s plus 1 over 2s square plus 3s plus 1. Let's suppose you have second order transfer function, and I want to create this in MATLAB. For that, you should know what are the types of variables that a MATLAB can store. You can have integers, you can have floats, you can have array, you can have structure. One of the class is an object. So a transfer function is stored as an object in MATLAB. So let me show you the method one. Okay, I will show the first method to create the above transfer function. One of the way is to simply write the transfer function in Laplace variable. For that, what we have to do, we have to just write the command pf like this. See, what I've written here is tf command. Tf command is basically the command for transfer function. Okay, short for tf. What I'm saying here is s, store s, a variable which has a transfer function in the Laplace variable s. So what essentially this command does, कि जो MATLAB में variables रहते हैं, any alphabetical variable, it will store this s as a Laplace s, and not any ordinary s. समझ में आया? This s is not any ordinary variable. This s will be reserved for Laplace variable. That's my first line. Okay. Once I write it, I can simply write the transfer function then. G of s, or let me simply write as g, because g will be stored as an object. It will be simply s plus 1, and in MATLAB you have to always take care of the brackets, over s square plus ts plus 5. Okay, and one more thing, these are on the left, you can see the line number also. तो मैं हर एक line पे एक terminator लगा रहा हूँ. Terminator is basically this column, which means when I run these lines of code, when I run this variable will not be shown, it will be just saved in the variable. Okay, we will just run this, but before I run, I have to save this. Let me save this by the name transfer function. Okay, let me just save this. So the file name is transfer function. So if I run this, see, I have created a transfer function whose name I have suggested as g. And what's the transfer function? S plus 1 over s square plus 3s plus 5. So this is a continuous time transfer function. If you see on the right, in the workspace is basically the space in which all of your variables are stored. See, I have two variables here. First is the variable that's s, given in first line number 5th में लिखा है. And the second variable is g. G is basically this. If you open, this is basically an object in MATLAB. It will have a lot of arguments रहेंगे. इसमें having a numerator, denominator, a variable in Laplace S, then some extra functions, then some names which I can assign. So this G जो है it's basically object variable in MATLAB, and it can have a lot of properties. जो मैं properties दिखा रहा हूँ. So this is one straightforward way to make a transfer function. Just 2 steps. पहले step में आप एक variable store करो in the form, मैंने यहाँ पे S use किया, and second step just write the equation. Any algebraic equation जो भी आपको लिखना होगा. ठीक है? This is method number 1. Another method to write to make a transfer function is to store the coefficients of numerator and the coefficients of denominator. जैसे अपने क्लास में पढ़ा होगा जब हम बनाते थे companion forms में हमारे पास a matrix रहता था, and a matrix used to represent कि हमारी transfer function बनेगी at the end, वो कैसे रहेगी. So इस method में क्या होगा, we will just store the coefficients of numerator. Let me just write. मैं बताता हूँ क्या है. ठीक है. I'm just storing 2 vectors basically. Let me write it as G2. See what I've written here. I've just stored a variable with the name NUM, which means the numerator, and I've stored a vector 1 1. ये basically इसका meaning ये हुआ, when I write this numerator and denominator coefficients, and when I use these numerator and denominator in the TF command, again, what I'm telling MATLAB basically is create a transfer function whose numerator coefficients are 1 1, which means this entry is corresponding to s to the power 0, and this is corresponding to s to the power 1. And denominator mein again, this is s square plus 3s plus 5. Let's look at here. यहाँ पे coefficients जो है numerator के 1 1 है, और यहाँ पे जो है coefficients of denominator are 1, 3 and 5. That's what I've written here. And इस transfer function को G1 लिख लेते हैं, and इसको G2 लिख लेते हैं. If you run this, this is exactly similar. G1 and G2 are same. So these are basically 2 different methods of writing the transfer function. Okay. Any questions so far? Any questions?
No, sir.
Okay. Moving on. This one another method एक है जिसमें हम we can write a transfer function. This is a more जो मैं method दिखा रहा हूँ तीसरा. This चूंकि आपको पता है कि जो transfer function रहती हैं उसमें certain properties of some transfer functions, like you have poles, you have zeros, and you have a gain. Let's suppose I give you a problem in which I tell you कि poles are this, zeros are this, and gain is this. Make a transfer function, which means you don't know the equation and you don't know the coefficients. You just know the poles and zeros, and from that you have to create the transfer function. So this method will be used for that. What I'm writing here will be clear. Wait. See, the first command I've written on the 14th line is tell me the zero of this G1 transfer function. Since G1 and G2 are same, what I'm written here, the zero command. The zero command is a function which extracts zeros from a transfer function. And I have on the output I have stored 2 variables, Z and K. So क्या होगा, Z में store होंगे the zeros of G1, and K will store the gain or the DC gains की हम बात करते हैं of this G1. Then I'm also storing another function by the name of pole, and I'm just in the input I'm providing G1, and on the output I'm providing small p. So p will contain the poles of G1, Z will contain the zeros of G1, and K will contain the gain of G1. And at the end I'm writing a line which means which has ZPK as the argument. This is a function in MATLAB which means 0, pole, and K. ZPK. It has 3 inputs: the 0, the pole, the gain, and on the output you can store a transfer function. By the way, जो functions मैं बता रहा हूँ, 0, pole, and gain, you can, if you know them, it's good. If you don't know them, you can use help command here. See, if I'm using help 0, you can get a little bit of documentation. 0 command, how does the 0 command work? See, I have written help 0. So it says 0 computes zeros and gain of a single input, single output linear system. So this is the command, this is the syntax that you have to use. Here you have to use square brackets, here you have to use normal brackets, and you have to use the keyword 0. And system is the transfer function which is already stored. And once you use this line, this will extract the zeros in Z, and this will extract the gain in this variable, which is G. Okay. So मैं क्या काम कर रहा हूँ? मैं जो already stored transfer function है G1, I'm extracting the zeros, the poles, and the gain. And from these, I'm again creating another transfer function, which will be same. So I'm just showing you, if you know zeros, poles, and gain, how you can get the transfer function basically. So again, if I run this, you see I am having G1 using method 1. Again, the same transfer function using method 2, which is using the coefficients of numerator and denominator. And another transfer function, which is again the same, but this time I'm using a continuous time 0 pole gain model, which means I have given MATLAB the information of zeros, poles, and gain. Then I use the command ZPK, and MATLAB created a transfer function by the name G3, which has the same numerator and denominator coefficients. Okay. And you can also see यहाँ पे जो variable store हुए on the right, you can see the gain is 1. Here are the poles. Or if I write P, the poles of the transfer function are complex conjugate. They are -1 and plus minus j something. And you're having also a 0 at -1. So this is how you define a transfer function. I have told you 3 methods. One is straightforward, simple equation के लिए, बस ये आपको ध्यान रखना on the brackets. Second method में coefficients रहते हैं, and third method में if you have zeros, poles, and gains information, you can get a transfer function using that. Okay. So after having a transfer function, you can plot basically a number of things about the system. क्योंकि transfer function known है, so it creates a lot of convenience for us, because जब transfer function पता है, so you can check anything about the system. Let's plot some things. Let's create some plots for transfer function same, and we can use any one of them, G1, G2, or G3. And let's create some plots to see the various dynamics associated with this transfer function. For that, I will create a plot, लेकिन उस plot के अंदर भी काफी plots रहेंगे. So what I will do, I will create a subplot. Have you used subplots before? हाँ, subplots कभी use किए पहले?
No, sir.
No, sir.
ठीक है. So I have to basically, let me just first write, then I will explain what I'm doing. Okay. क्योंकि ये चीजें थ्योरी वाइज आपको पता होंगी, definitely. बस मैं आपको दिखा रहा हूँ कि how you can use this MATLAB for visualizing things, basically. Let me just copy this. Getting there. Pick another. Then I can plot a step. मैं बताऊंगा मैं what I'm writing. This G1 grid. Or I can use another 5. I can plot impulse. The functions जो हैं they are self-explanatory. आप देख सकते हो कि जो commands हैं या जो functions हैं उनके names भी वही हैं कि जो ये करने वाले हैं. I can plot Nyquist. I can use the last one for impulse. See, यहाँ पे मैंने I've used a bunch of lines for creating plots. This basically means a subplot. जब भी आप MATLAB में कोई figure plot करते हो, you know it has 2 coordinates x and y. If I talk about 2D plots, तो मैंने क्या काम किया? I'm just creating a function which has the name subplot. Again, if you don't know, you can go help subplot. it will give some information about subplot. How do you use subplot? What is the use? It creates axes and titled positions. So it has 3 arguments: subplot, M, and P. M is basically it breaks what subplot does. It breaks your figures into smaller figures. ठीक है? तो मैंने एक figure create की, which has 2 rows and 4 columns. ठीक है? उस figure के अंदर 2 rows होंगे और 4 columns होंगे. So which makes 4 into 2 is 8 elements. So 8 plots will be there in a single plot. Okay? There will be 8 smaller plots within a big plot. And then is the first argument. First argument says the first plot among the 8. That is a PZ map. PZ map, if you see, help PZ map, it basically plots the poles and zeros, computes the poles and zeros of the dynamic system. So I've said the MATLAB ki ab G1 a transfer function already stored here. Just plot the poles and zeros on the real and the imaginary axes. Then the second plot among the 8th, just plot the root locus. Okay. On the 3rd, just plot the Bode plot. On the 4th, just plot the step response. These are basically functions which are already defined in MATLAB. This PZ map, R locus, Bode, step. Similarly, on the 5th, I'm just telling MATLAB to plot me the impulse of this G1. On the 6th, plot me the Nichols. Let me just run. आपको समझ में आएगा मैं क्या कह रहा हूँ. You will see a bunch of plots. Yeah. This has not come. Wait. सारे 8 plots नहीं आए. 1, 2, 3, 4, 5, 6. Okay, I can go on. I have plotted PZ map, root locus, Bode. I have plotted step, impulse, Nyquist, Nichols. 241 पे I have plotted PZ map. 242 R locus. 243 is a Bode plot. 244 is a step. Okay. 245 is an impulse. 246. This is a line missing here. 246, I'll be having a Nyquist. 247, I'll be having a Nichols plot. And let me just grab one more. 248, which is the 8th plot. And let me plot. I will explain this, okay? Let me just run this first. Now you are seeing basically 8 plots within a plot. ठीक है? मैंने 8 plots plot किए हैं in a single plot. That's why मैंने कहा था 2 rows and 4 columns. ठीक है? See, when you know the transfer function, you can plot a number of things straight away from MATLAB. See, I will just zoom it a bit. The first plot you are seeing is the pole zero map, which जब भी मैं दिखाया था ना 2 poles हैं here crosses में, and you are having 1 0. This is basically real axis sigma, and this is j omega. So you can see this is 0 0 point here, 0 0 point. So you can see MATLAB has plotted the poles and zeros on the complex map. This is the first. Second is the root locus. You know, root locus is basically the plot coming from this as we vary the gain k. So this is the locus of the 2 poles. See, this green is the locus of 1 pole. This is moving from here, then going to here. Sorry, the locus should start from the open loop pole, this one. Then it moves this green path and goes to infinity, left infinity. And the second pole, which is up top, it comes down and it's going towards the 0. This is the root locus for varying k. The third plot is the Bode plot, which हम discuss कर चुके हैं lab में, of the same open loop transfer function G1. This is the magnitude plot, this is the phase plot for running frequencies. The fourth plot is the step response. MATLAB has used a step input for the system, and it has plotted the step response. See, and from the plot you can see certain things about the system. Okay. This is amplitude versus time. Next, we're talking about impulse response. Just the input has changed from step to impulse input, and this is the impulse response for some arbitrary time. MATLAB has basically जब मैंने command लिखा था, I have not provided time. So MATLAB has automatically taken the time as 3.5 here, and if you see यहाँ पे 5 लिया है, तो so that ताकि मैं figure अच्छे से देख पाऊँ, because it has seen कि यहाँ पे transients has died out, then steady state, so it has plotted up to 5, but we can go beyond that also. यहाँ पे 3.5 तक plot किया गया है. Next diagram is the Nyquist diagram जो आप पढ़ते हो. I don't know whether you have अपने इसके बारे में कुछ पढ़ा होगा. Nyquist diagram में हम we plot the real and imaginary part of g j omega into h j omega. So this is the real part and this is the imaginary part. And यहाँ पे आपका है, यहाँ पे जो है this red one. If I move this, you're having this -1, and in Nyquist we are interested in this -1 plus j0 point, isn't it? And the next plot is the Nicholas chart. Nicholas chart is basically a simplified version of Bourdais plot. See, Bourdais में आपके पास रहता है magnitude plot versus frequency and phase plot versus frequency. What you can do is you can plot magnitude versus phase and remove the frequency. This is Nicholas chart. You're having open loop gain and open loop phase. I've just removed the frequency and I've plotted one with other. This is the Nicholas chart. And on the last, I've again plotted a step response. But the difference is the first step response is the response for open loop system, open loop G1, and the second is the closed loop system. I have closed the loop with G1 with a unity feedback, and then I have applied a step response. And the command, if you see the command, let me just say here, जो मैंने command use की है, the command is feedback. It's used like this, feedback. Then the first argument is the transfer function, जिसका आपको feedback लेना है, and the second argument is the value of the feedback that you want to give. यहाँ पे मैंने 1 लिया है, which means it's a unity. Let's suppose आपको feedback में you're having another transfer function, which is h of s, जो हम लिखते हैं ना in the block diagram. So h of s will come here, and g of s will come here. And by default, MATLAB uses a negative feedback. It provides a negative feedback, but you can change it to positive also. And this function feedback closes the loop. And of that, ये जो मैंने highlight किया यहाँ पे, feedback of, let me just grab this and write it here. This is the transfer function of closed loop system, and G1 was for the open loop system, which is open loop का था, with unity feedback negative, it becomes this. And पहले मैंने इसका step लिया था, अब मैं इसका step ले रहा हूँ. I mean, दो plots हैं for two different steps. So what you can say about the stability? See, you're having a range of plots in front of you, and आपको सिखाया गया है, if you are having simple systems like first order system, second order system, how you can sketch these plots using hand, isn't it? आप pz map डाल सकते हो, आप root locus डाल सकते हो, even you can plot Bourdais, you can draw the step response of open and close. You can also draw impulse response. Just forget about these two. तो आपने ये चीजें सीखी हैं for simple systems, first order system, second order system. But MATLAB can be used to plot these things for a high dimensional transfer function. Let's suppose आपके पास transfer function जो है उसमें 100 poles है and 50 zeros है. So that cannot be drawn using hand. So MATLAB का आपको use करना पड़ेगा वहाँ पे. अच्छा, what's the stability? Can you comment about the stability? Stability can come from any of the figure. If you see on the left, both the poles are on the left half, isn't it? आपका origin यहाँ पर है. Here is the origin. So both the poles are on the left half, and both of them are having what? Their complex conjugate. So it's a stable system, and this is also verified by the step response. See, एक rise होके, it's just going settling somewhere. Okay, this is a prototype second order system. Even from the Bourdais, you can verify it's a stable system, even from the root locus, and from the, if you see the step response of the closed loop system, it's again very stable. Also the impulse response. Okay, so मैंने आपको अभी तक सिर्फ सिखाया how do you create a transfer function and how you can extract meaningful information from that transfer function. ठीक है? Okay, moving on. अच्छा, before we jump to the basically lab जो हमें करने वाले हैं, उसके लिए ये सारे prerequisites हैं. Okay, I will just show you one more thing. आप उसके साथ easily connect कर पाओगे, which is the time domain. आप अभी पढ़ रही हो ना स्टेट स्पेस मॉडलिंग, isn't it? तो ये जो था अभी तक हमने बात की, दिस वाज इन फ्रीक्वेंसी डोमेन. और अभी तक frequency domain की बात कर रहे थे, इसमें हमने ट्रांसफर फंक्शंस देखी. What if you want to use MATLAB for time domain modeling, which is the state space modeling? So you can, in MATLAB, you can very simply convert your transfer function into state space. Let me show you how. The command is tf to ss. tf is the transfer function which we have used. Ss is the command for state space. So the formula tf to ss means convert transfer function to state space. It has two input arguments. First is the numerator coefficients, which I've already stored as variable num, and the denominator coefficients. Okay? You have to provide numerator and denominator coefficient to the transfer function. And the output में इसमें 4 variables है. Can you guess what will be the 4 variables in this command? Anyone?
A, B, C, D, sir.
Yeah, it will be A, B, C, D. Because what you're expecting a state space model, and this command will transform your transfer function to the state space model with A, B, C, and D. See, if I run this, just this part. See, this was the transfer function G1, and MATLAB has converted, because the second order system, it has converted into A 2 by 2, this B, this C, and this D. And these A, B, C, D variables are also stored in the workspace. You can use them anytime. Okay, so it's how आसान है MATLAB में if you are switching from time to frequency domain. Otherwise, आपको जो है you have transfer function और आपको पूछा जाएगा कि ABCD extract करो. So you have to do a lot of computation, isn't it? Even if you go from state space to transfer function, वो पूरी formula जो लिखते हैं CSI into A inverse plus B. तो हुआ क्या है, जो TF to SS command है, उसमें वही formulas use किए गए होते हैं जो हम on paper use करते हैं, that CSI minus A inverse or the going back. So the MATLAB community has developed this function, but essentially it does जो कि आपने already पढ़ा हुआ है. So these formulas come from that. ठीक है, तो अभी तक मेरे पास खाली ABCD models हैं, but I don't have a state space model yet. So to create a state space model, I have to use the command SS. इस तरह मैंने transfer function में I have used the command TF. For state space, I have to use the command SS. And this SS command has 4 input arguments, which is A, B, C, and D. जो हमने अभी तक extract किए. And on the output, it will store a state space model. Let me just rename it as system, SYS. I will run this, and it has created the system. मैंने क्या काम किया, अभी तक जो ABCD थे, A, B, C, and D, they were just normal matrices. MATLAB ने इसको denote किया as some random ABCD. But I have, in this line, I have been telling MATLAB that these A, B, C, D are not any ordinary matrices. This is the system matrix. This is the input, control, input, and output. And it has stored it in this system. अगर आप देखो, this system is again an object file, and it's having these A, B, C, D as matrices. Then you're having a number of properties, like you're having this input. How many inputs are there? How many outputs are there? You know, state space model can be defined for multiple inputs, multiple outputs. यहाँ पर जो था मैंने कैसे extract किया? Extracted is from the transfer function, but transfer function is always defined for single input, single output. So यहाँ से जो मैंने extract की information that have been stored in A, and if you see B is a vector, so is C, which means it's a single input, single output system. Had it been a NEMO system, so we have multiple columns for B and multiple rows for C. वो तब आएगा कि आपके पास multiple transfer functions होती for a single system. ठीक है? So this is how you create a state space model. You use the command SS, and for a transfer function, you use the command TF. Okay. Again, you have the state space model now. What you can use the state space model for? The first thing that will come to your mind. State space model से क्या information निकाल सकते हो? Can you find the eigenvalues of A? Very simple. Just use the command EIG, short for eigenvalue. If I run this, see, these are the eigenvalues, which are basically the poles. मैंने P से store किया था ना? See, these are exactly the similar. So the poles of the transfer function are the eigenvalues of matrix A. और हमने देखा था from the PZ map. फेजर मैप हमने देखा था कि पोल जीरो कैंसिलेशन नहीं हो रहा था कहीं पे भी, सो द पोल्स आर एग्जैक्टली इक्वल टू द आइगन वैल्यूज जो कि है, ठीक है। दिस इज द फर्स्ट कमांड दैट यू कैन यूज टू यू नो डू थिंग्स। अच्छा, इसके अलावा व्हाट यू कैन यूज द स्टेट स्पेस मॉडल फॉर, कैन यू जब आपको हमने असाइनमेंट्स दिए थे, इफ यू रिमेंबर, वी आस्क्ड यू दिस, represent a state space model in different companion forms, isn't it? So जो हमने यहाँ पे देखा ना in this A, B, C, D, this is, if you see, this is not in any standard companion form per se, it's in a general form, but we can convert this structure into a special form which is known as a companion form. तो आपने पढ़े हैं first, second and Jordan's, so we can quickly make the system in any form. So the formula of the function is canon. Canon means companion form or canonical. Sorry, canon is for canonical. ठीक है, इसमें जो है input has two arguments. First, the state space model that you want to convert, and the type of companion form. Let me just write here companion. I'm using this function canon. पहला argument है जो state space model I want to convert, and I want to convert into a companion form. And the output may just name the variable. Let me just name it as system2, let's suppose. So system will be converted into system2. Okay, let me just run this. See, this is the system2. Okay, कौन सा companion form में इसने convert कर दिया? Isn't this the second companion form in which the coefficients are written on the column, the last column, है ना? Or B is 1 here and C is 1 minus 2. So this is second companion form basically. इसने जो हमारा, if you compare to previous A, see A was -3, -5, 1, 0, and here the A is 0, -5, 1 and 3. यहाँ पे 2 by 2 example हमने लिए. If you had been a big example n by n, you will see it will be 0 and you'll be having ones on the lower diagonal, and on the last column you will see the coefficients of the denominator written in reverse order with the minus sign. ये वही है. अच्छा, I can also define another. Let me system3 ecosystem ले लेते हैं, and again I am converting my system, but this time I'm converting into different companion form. Let me just write function which is model. Okay. This time I'm converting my system into model form, and that I'm storing it in system3. You know the eigenvalues, you know the poles, they are already stored. See, यहाँ पे हैं हमारे poles P में. These are your poles, है ना? So these poles will be used to form this system3. This is your system3. It might look a little bit different than you are used to, क्योंकि जो हमने Jordan's आपको दिखाया था, Jordan's canonical form, उसमें on the diagonal form, on the diagonal entries you're having what? The poles or the eigenvalues, and rest are आपने देखा होगा zeros होते हैं. लेकिन यहाँ पे जो poles है, that are complex conjugate, isn't it? तो यहाँ पे जो diagonal है उसमें real part store है, और जो non diagonal है उसमें frequency stored है, the imaginary part. See, if you want some detailed information on this, you can use this help canon. So the function goes like this: canon, the system, and the type. And you can define a model representation. You can define a companion representation, and by default it gives you second companion form. But you can extract the first companion form by taking just the transpose of A, B, and C. See, this is an extra information कि कैसे होता है. Or what you can do is also you can go to the reference page. This will redirect to a more detailed discussion on this canon. यहाँ से you can see, and from this you can see some examples also. See, this is a transfer function, okay, already stored. तो उसने क्या काम किया है? He has used the function canon, and he has converted this transfer function first of all into a modal decomposition. See, this is the modal form. तो पहला जो ब्लॉक है, जो जॉर्डन्स ब्लॉक है, so इसमें पोल्स जो हैं, देखो पोल्स जो हैं, they are 1 repeating, and here are the complex conjugate part. Then you're having a single pole at 2. ठीक है, ये repeat नहीं हो रहा है. Then again you're having a repeating pole. That's why another block आ रहा है, ये वाला block. Then again you're having a different value. Sorry, this is repeating, and you're having it like this. So this is how a modal form looks like. But you can create it. अगर आपको Jordan exactly चाहिए, that can be also done. And these are some extra examples. Similarly, companion form. Companion form इसमें कोई example भी है? No, this is just an example for modal. Okay. So similarly, you can convert it for a companion form. This is the basic representation for the modal form. Lambda 1 comes here, single pole. Then sigma comes here, and j omega comes here. Then another pole, non-repeating, lambda 2. This is how modal form is represented. And this is the second component form that I was talking about. Second component form में आपके पास diagonal में zeros रहेंगे, sub-diagonal में 1 रहेंगे, and the coefficients of the denominator here will be stored on the last column. जो आप पढ़ते हो. This is the second component form, और वही हमने use किया. Then if you want to extract, let's say, first component form, just take the transpose of A. Isn't it? So मैंने system 2 बनाया था ना. System 2 was second component form. And if you want to see just the A, you write the command system 2 dot A. This will just tell you what is the A inside the system 2. And if I transpose this, let's say dot A, and I just give it a transpose command. See, this is the first component. So you have seen this property that first component, second component basically complements of each other. So you can derive any component form. You can derive the modal form. और मैंने आपको दिखाया था command for eigenvalues. Simply eig of A. Or if you see a detailed description of this I command, it not only gives you the eigenvalues, it will also give the eigenvectors. Its general presentation जो मैंने शायद आपको कभी क्लास में दिखाई थी, this form. V, D equals I of A. If you have any matrix A और आपको eigenvalues और eigenvectors निकालने हैं, just use this command. So in V, it will store the eigenvectors, and in the D will be basically a matrix. और उस matrix के diagonal पे आपको eigenvalues मिलेंगे. और V will be an eigenvector. इसके columns जो होंगे, it will be a matrix. उसके columns जो होंगे, that will be eigenvectors. And these V, D, and A follow this relation. AV equal to VD. जो हम पढ़ते हैं ना, AV equal to VD, और A small v is equal to वहाँ पे यूजुअली हम लिखते थे lambda d. But mind you, यहाँ पे जो है this matrix vector cannot be producted. इसलिए यहाँ पे V into D लिखा गया है. Because both of them are matrices. वहाँ पे हम दिखाते थे कि lambda is a scalar, but यहाँ पे जो lambda है that's stored in this D, and D is a, if we use this command, let's suppose we use this command, copy it here, and I will just मैंने ये command copy कर ली. See, जो V है, the first जो column है, that's an eigenvector corresponding to the eigenvalue this, जो कि pole है पहला. और जो दूसरा column है of this V, that's another eigenvector corresponding to this pole. In theory, we write this D as lambda, but MATLAB stored it as a matrix, and the matrix के जो diagonal terms है, उसमें eigenvalue store रहते हैं. ठीक है? This is a simple thing to do. अच्छा. एक और चीज हम कर सकते हैं, because we have the state space model and we have stored in a number of ways. System 2 and system 3. What if I tell you, अब अभी पढ़ ही रहे हो, the controllability and observability, है ना? अपने क्लास में I think you have started observability now. तो controllability observability आपने पढ़ा. This is the command. Command is CTRB, short for controllable. If you run this, see, this is the matrix. अगर आपको बोला जाए बनाने को, so this is basically B and this is AB. For 2 by 2, this is your controllability matrix. And when you talk about the test, let's suppose I ask you, is this system controllable? कैसे पता चलेगा? How do you find the controllability test of a system? हाँ, पढ़ाया सर ने. How do you?
values of B.
कंट्रोलेबिलिटी ग्रामी एंड कंट्रोलेबिलिटी मैट्रिक्स या फिर
हाँ,
आइगन
there are basically n number of ways to do it. आपने सर ने आपको 2-3 चीजें दिखाई होंगी, 2-3 तरीके दिखाए होंगे to find the controllability observability test. A simplistic way I can do it by checking the rank of this matrix. Or in a better way, if I just store this in a C, पढ़ते हो ना कि or not in C. C is already taken, isn't it? C is taken for C matrix. आपको ये ध्यान रखना है MATLAB में. Variables should not be overlapping नहीं होना चाहिए. C is already taken. Let me just take it as CP. CP for controllability matrix. Okay, and OB. This is the command for observability matrix, OBSV, of the state space model. Okay. So when I run these two commands, you will see the CP and मैं यहाँ पे एक जो है I'm just uncommenting this and ताकि ये आपको दिखे and इसको मैं लगा रहा हूँ. See, this is your controllability matrix, this is your observability matrix, and आपको पूछा जाएगा कि whether the system is controllable or not. So you have to just check the rank. If this matrix is full rank, which means it's having independent columns or independent rows, which means it's passed the controllability test. So in MATLAB, we use rank, simply rank of any matrix, and the matrix is CT. And for observability, I will write the rank of the observability matrix, which is OB. So if the rank is 2, which means it's controllable. And if the rank is 2, again, for OB matrix, which means it's observable. Simply, I just run this command line. See, rank is 2. और उसमें इसको मैं अगर store करूँ in check controllability, and I store it in variable check observability. Okay, and if I run this section only, see, it says the rank of controllability matrix is 2, and the rank of observability matrix is also 2, which means the system has passed. It is controllable and it's also observable. So हमने एक ऐसा system लिया था, this system which was controllable and at the same time observable, and इसके आपको poles भी पता चल गए, eigenvalues भी पता चल गए, eigenvectors भी पता चल गए, transfer function already known है, and you have different canonical forms. तो आपको you can relate, जो अभी तक आप पढ़ रहे हो ना, you can relate these kind of things with MATLAB. अभी तक कोई question, anything so far before we move on? हाँ, कोई क्वेश्चन कहीं पे, डाउट कोड में या कंफ्यूजन कहीं पे?
नो सर.
एवरीथिंग क्लियर?
सर
ठीक है. सो लेट मी मेक अनदर स्क्रिप्ट and let me save it by the name linear system. Okay? Now we are going basically, any question?
सबप्लॉट में एक डाउट है.
Okay, subplot. See,
सर वहाँ पे आपने 2-4 दिया था ना, तो
क्या?
वो नंबर्स मतलब क्या है?
मैं बताता हूँ. See, I will tell you. See here, I'm saying MATLAB to create a figure and divide that figure into 2 rows and 4 columns. See, 2 rows and 4 columns. आप समझ में आ रहा है? And this is the first plot. So 2 rows, 4 columns, and the first plot should be PZ map, which is here. Then 2 row 4th column का जो second plot होगा, क्योंकि 2,4 becomes basically 8 plots होंगे, और उसमें जो second place पर जो plot होगा, that should be an R locus plot, which is here. तो समझ में आया कि how this 2 and 4 are relating?
हाँ सर
हाँ,
सर तो अभी
dividing-
अभी मतलब अगर मैं अभी मतलब आर लोकस का जो प्लॉट आप बोल रहे हैं 2 4 पे बोल रहे हैं इन केस है मतलब मैंने 2 4 के बदले और कुछ डाल दिया तो क्या होगा?
हाँ, let me just create another figure for you. See, I'm having another figure. Okay, it's blank figure now. See, I want to मुझे मान लो एक प्लॉट क्रिएट करना है साइड बाय साइड. लेफ्ट साइड एक फिगर होनी चाहिए, राइट साइड एक फिगर होनी चाहिए. आई विल यूज सब प्लॉट. क्योंकि लेफ्ट राइट आई वांट वन फिगर ऑन लेफ्ट, वन फिगर ऑन राइट, सो इट्स हैविंग रो ओनली वन, बट कॉलम उसमें दो होंगे. If I run this, it create a blank plot, row 1 and 2 columns. If I write now second entry, तो रो आप इसको ले लो एज जैसे हम लेते हैं ना मैट्रिक्स में रोज एंड कॉलम्स. So this corresponds to the number of rows and this corresponds to the number of columns. And this total number of elements जो होंगे, that's product of rows and columns. And this last entry determines the element number. उसमें ठीक है. Subplot 1 to be create a figure like this, left and right. Left and right is 1 row and 2 columns.
Sir, basically length of axis.
You can also take it as length of axis. See, in order to visualize, I have to show you some. Let's suppose 2 rows, 2 columns, and 1. Let's say figure 1 way, and then 2. Let's suppose 3. Let's suppose 4. See, I've created a plot with 2 rows and 2 columns, which means 4 plots only. 2 and 2. समझ में आया? This is by the way an extra thing. ये it's not necessary for control systems. ये मैं बस plotting कर रहा हूँ ताकि देखो पहले plot में मैंने 8 plots किए थे, है ना? I plotted 8 plots. In order to avoid 8 separate figures, मैंने एक ही फिगर में सब कुछ प्लॉट किया, बिकॉज पहले ही मुझे पता था कि मैं 8 प्लॉट्स लाने वाला हूँ. नाउ 8 प्लॉट्स यू कैन अरेंज इन 2 rows, you can arrange in 3 rows also or 4 rows. तो मैं यहाँ पे अरेंज किए in 2 rows and automatically वो 4 कॉलम्स में अरेंज हो गए. And this is 241, 242, 243, this is 244 and so on. Okay?
Yes, sir.
Okay, moving on to, this was basically a prerequisite. मैंने आपको सिखाया अभी तक ट्रांसफर फंक्शन कैसे बनाते हैं और स्टेट स्पेस मॉडल कैसे बनाते हैं. Now we'll move on to the lab. जो हमने अभी तक लैब में मॉडल्स दिए, they were basically first order systems, second order systems, और हमने शायद एक एग्जांपल ली थी of third order system. So जो हमने systems लिए थे, how do you simulate those systems in MATLAB? आपके पास मैंने दिखाया था, we used oscilloscope basically. हमने oscilloscope से measurements लिए थे from the input, from the output, और मैंने कुछ systems, dynamical systems लिए थे, first order के भी, second order के भी. So let's just simulate some systems. और मैं जो आज हम बना रहे हैं ना scripts, I will just share these scripts with you, okay, at the end. मैं आपके GCR में या WhatsApp पे I will just share these scripts, and if you run them on MATLAB, we can just modify these plots or modify this code further, ताकि आप और सीखो, ठीक है? So यहाँ पर हम linear systems simulate करेंगे, ठीक है? So let me start with first order system. हमने लैब में 2 kind of first order systems देखे थे, if you remember. One is this, and another is this one, if you remember. One is an integrator, k by s, transfer function है, और another transfer function ली थी हमने time zero, time constant form, k upon st plus 1. Both of them are first order systems. If you remember, जब हमने पढ़ा था ना linear system simulator. Wait, I will show you. This is the manual. Why is the block diagram? ये हमने पढ़ा था this k by s. We saw this response to a step input. ये कुछ ऐसा आता है, ramp. And we also saw this kind of system, k by st plus 1. If you apply step input, it behaves like a first order system. It's rising and settling somewhere. और मैंने आपको example भी दिखाई थी कि this corresponds basically to an RC circuit or an RL circuit. लेकिन हमने वहां पे क्या काम किया था लैब में, वी डिडंट प्रोवाइड स्टेप इनपुट बिकॉज यू कैन नॉट प्रोवाइड स्टेप इनपुट। इफ अगर स्टेप इनपुट दोगे तो कॉन्स्टेंटली राइजिंग कर्व होगा। इंस्टेड वी प्रोवाइडेड अ पीरियोडिक इनपुट, वी प्रोवाइडेड अ स्क्वायर वेव of some known frequency, and at the oscilloscope we saw a repeating pattern for both the systems. So let's just try this, both of them. See, you know how to create transfer functions now. See, if I simulate this, first of all I have to store this transfer function k upon s. So how will you make this k by n s? Let me use method number 1 जो मैंने दिखाया था। ये रहा आपका Laplace variable, and let me just store this, and instead of k I would have this k1 and this I would have this k2 ताकि ये different चीजें हैं। Let me just store this k. This is a scalar, I can store it by any number, let's say 0.3. Okay, now let me just create a transfer function by the name system1. Okay, and the transfer function is simply k1 upon s. I personally also prefer to use this kind of method for creating transfer functions. It's very simple. आपको बस एक Laplace variable store करना पड़ता है s, then just simply write the equation. जो equation रहती है उस equation को replicate करना है. Okay, and इससे पहले we will just clear everything and close everything. And this is a good practice. जब भी आप कोई नया code लिखो, just clear the previous variables already stored, or close any figure, or clear the command window. Okay, this is just for clearing things first. Then I start with these lines. और मैं साथ I will just write the comment, create a transfer function. Okay, so ये तो मैंने create कर दिया system1. What I will do, I will use a command here. See, मैं यहाँ से क्या काम, what I can do is I can just plot the step response. मैंने आपको दिखाया था step response is used by using the function step, step. अगर मैं step command दूंगा, I will see a function like this. Let's try. And let's save this and run this. See, similar output जो है, it moves like a ramp. लेकिन हमने लैब में we didn't provide a step input. हमने step input नहीं दिया था. To simulate a step input, we used a periodic square wave. ताकि आप यहाँ पे जो है खाली आप rising edge देख पा रहे हो. But जब negative step आएगा, इसमें एक negative step भी आ रहा है ना. जब negative step आएगा, the value goes minus kt. So this has to fall then. तो वो pattern देखने के लिए you have to provide a positive step and a negative step simultaneously. So let's simulate that scenario. See, let's remove this line. I will first create a signal because in MATLAB you cannot MATLAB makes square signal by default store नहीं रहती like a step. You have to create that square signal first. Okay, I will use a command GENSIG, which means generate signal. Okay, a block भी रहता है Simulink में, or you can use a code simply GENSIG. Okay, it has various arguments. First argument is the type of signal you want. I want a square signal to be produced. Or then it follows the further commands. If you type help generate signal, it will tell you the extra arguments. See, type में you can have a sine, square, or a pulse, and I'm using a square. Then you're having this tau. For extra information, you can go to reference page. See, if you want to create a square wave like this, just write the square term. 5 is basically the time period. See, after 5 it's repeating. 5 के बाद ये फिर से repeat हो रहा है. 30 is the total time that you want. Okay, and this 0.1 is basically the sample time. कितने samples के बाद आपको नया एक value चाहिए? He's using a sample of 0.1. So every 0.1 seconds he's generating a point on this. This is not a continuous plot. This is a plot formed by various points. और हर एक point की जो distance आपस में, that's 0.1. That's the meaning of this whole line. और जब आप ये run करोगे, the output is stored in u and t. The t is basically जो time रहेगा, these values, एक vector होगा, This will be a vector from 0 to 30 in the steps of point 1. And this u is this one, the y-axis. जो values रहेंगे ना, जो height रहेगी at every time, that is stored in u. So once you have this command, you can use this u now. This u is basically this amplitude. So let's use this command. Let me create a square. Let me use a more fine square, okay? और मैं जो signal है, let me just use y comma t. Okay, and I will terminate this. In comment, I will write a periodic square wave because we are like it's visualize करने के लिए periodic square wave. Okay, then let's take another system, this one. Okay, before that I have to create this k2 now. Let's suppose k2 is some random constant from change करेंगे आगे. And I have also stored this t constants and k2 and p. So let's suppose t is something 0.4. Okay. Now I will create this system 2 with the transfer function k2 upon s into p plus 1. But you have to keep it in brackets. Okay. Otherwise, this is the numerator. This is the whole denominator, and s is small, not the capital S. Okay. So जो हमने अभी तक की periodic square wave बनाई, you will feed the square wave to both the systems. So let me just grab it and move it upsides. Okay. यहाँ पे I have created my system 1, और यहाँ पे I have created my system 2. It's a good practice to rename everything in your code, ताकि when you give your code to anyone, तो वो वहाँ से उसको ना replicate कर पाए या वहाँ से understand कर पाए कि code में हो क्या रहा है. ठीक है. Now the command used to simulate the system is LSIM. LSIM is basically linear simulation. It's much similar to a step. जो मैंने step दिखाया था ना, for step or impulse or R locus. Another you have function LSIM. This is basically to simulate any transfer function for any kind of input, not only for predefined step or impulse. For any random input like this, you can use command LSIM, and it has argument. System itself, जिसको आपको simulate करना है, and I'm simulating system 1 with the input. Input is y, and the time period is t. It is the system 1 is this output y is this, and this time is this. This will simulate the system for this input and this time, and the value or the answer will be stored. इसको हम store नहीं करते हैं, इसको सीधे plot ही कर लेते हैं. ठीक है? We will just plot this, and अभी तक जो है रन कर लेते हैं. Let me just run this. This is not as per expected, क्योंकि you see जो input है that's in gray. It goes from 0 to 1. Basically जो input है वो switch नहीं हो रहा है. Input जो है positive में ही रह रहा है ना, 0 to 1, then going 0. जो input है that should go in negative as well. It should go to -1 also. Then this will drop. तो एक small adjustment करनी पड़ेगी. Let's suppose y minus 1. I'm just multiplying it with a. It's kind of basically amplitude change कर रहा हूँ. See, what I have done is basically I have forced it to go from 1 to -1. अभी तक ये 0 से 1 तक जा रहा है. तो I have 2 times increased its amplitude, and this is the input. And just like oscilloscope is updated, this is the basically this. ये ध्यान से है. तो ये हमने सिमुलेट किया k/s ट्रांसफर फंक्शन, और हमने जो एक्सपेरिमेंट किया था, if you remember, we talked about this effect of k. ये जो ट्रांसफर फंक्शन is k/s, it has no t part. This is just integrator, and you can simulate the effect of k here. See, let me show you how. So यहाँ पे ले लेते हैं इसको. यहाँ you have running parameter k, क्योंकि simulator 1 में k है ना. You can just right click on it and or this k1 मैंने 0.3 लिया हुआ है ना. I can do it. System 1 k1 is here. or let me do it one thing first. Before I run it for multiple case, let me just simulate system 2 also. System 2 को भी simulate कर लेते हैं. So I will copy this line, paste it here, and I will create another figure. Separate figure लेंगे, उसमें system 2 को simulate कर लेते हैं. ठीक है? So run this. See, when you are having a comma error, तो error आपको command window में दिखेगा, and you have to basically interpret the error. The error says there is an error at line 15, which is this line. It says undefined functional variable system 2. There is no function by this name. The function is _2. So I have to use this. Okay, this is how you interpret errors and correct them. इसको run करते हैं. See, I have two figures, and this is here. हमने देखा था lab में first order systems of two forms, integrator and K upon ST. So a decreasing trend, then followed by a positive trend. And now I will just, form this effect of K and T. मेरे पास जो second transfer function है, इसमें दो unknown, दो constants हैं, K2 and T. See, if I do one thing, I will just change this K2. Wait. I will just grab this value, जो मैंने 0.7 randomly use किया था. I will just right click and increment value and run section. ये जो command है, what it does is, अगर आप click करोगे, you will get a block like this. See, it has a number, currently it's 1, and you're having this plus minus. If I press plus, it will add 1 to this number. 0.74 plus 1 will be 1.74, and it will evaluate the whole thing. But I'm not evaluating at 1. मैं इसमें add नहीं करूँगा 1, but मैं just add it 0.2. Small increments देते हैं. ठीक है? I will just increase this K to 0.2. इसको बंद कर लेते हैं. I'm just concentrating on this figure. And if I run this, it's creating a separate figure. Wait, I will close this figure. I will just comment this out. और इसको वापस पुरानी वैल्यू पे ले लेते हैं. 0.7 क्या या उसके थे मैंने 74. Anything will work. So I will just increment it in the steps of 0.2. See, this is your figure. If I increase this again with 0.2, it's giving me again a separate figure. See, why is it giving me separate figures? Okay, because I'm using LSIM twice. Let me just close this first system. I'm concentrating only on the second system. Okay. इसको मैं फिर से ले लेता हूँ 0.5 and see, this is your figure. And now if I increase my K, you see the amplitude is increasing, isn't it? जितना मैं K बढ़ा रहा हूँ, its amplitude is increasing as expected. But यहाँ पे जो मैं more interested हूँ, that's on the steady state error, and I'm more interested on the rise time. ठीक है? For that we will not change K, we will change this T. This T is used here. This is your figure. Let's suppose I'm increasing the values of 0.2. See, मैं बढ़ा रहा हूँ T को, and if I'm increasing T, this is becoming more of a ramp signal now. But I'm decreasing T. Let me show you for decreasing T. See what will happen for decreasing T. Wait, this should not show me a separate figure each time. कुछ कहीं पे कुछ गलत हो रहा है. Generate a signal Y K system, then KT, then system 2 is being created, then LSIM system 2 Y comma T. See, I will just decrease this K. and you will see as I'm decreasing this k, this is becoming a step input. Sorry, this is following the input. So as t goes down, the steady state error will go down, and the rise time, if rise हो रहा है ना, it will become much faster. This was what I observed here. See, if I show you this table, यहाँ पे कहीं पे तो table था. This one, basically I'm simulating this scenario. I'm just increasing k or decreasing the t, and if you decrease the t, you will see this is steady state error कम हो रहा है. This is इससे आपको ये पता चलेगा कि as we decrease tau or increase k, your system will follow the input basically. क्योंकि कम हो रहा है, so this is becoming the input itself. So वही यहाँ पे हो रहा है. See, for very small t, यहाँ पे t 0.2 है, and when I decrease this, अब t 0 हो गया. So I should not have used 0.2, I will use 0.02. छोटे-छोटे increments में इसको कम करते हैं. See, जितना मैं t कम कर रहा हूँ, this is becoming the input. और बहुत कम करके, it exactly becomes the square wave. And similar is the effect on k. अच्छा, यहाँ पे inputs outputs इसलिए match हो रहे हैं because k is less. If I increase this k, its amplitude is going up, and it will become exactly the input for some k, which is 1. So as I'm approaching k1 and t0, that's making it a square wave basically. And for some generic k and t, let's suppose this one, this is the thing that you observed in the oscilloscope, this thing. So when you're having some tau, this will be the time that will be taken. यहाँ पर आप काम कर सकते हो. You can check the peak response. नहीं, वो तो आप स्टेप में देखेंगे. That will see step, क्योंकि यहाँ पे you're having a periodic. और मैंने कहा था आपको जब लैब थी कि we only focus on one cycle. जो एक cycle में हो रहा है वही बाकी cycle में फिर repeat होगा. So you could have, instead of LSIM, I can also do a step of system 2. Okay. This is basically just a single cycle. वहाँ पे step में हम बस single cycle देते हैं. तो यहाँ पे if I now decrease t, यहाँ पे आपको ज़्यादा समझ में आएगा. If I decrease t, see, I'll use the command hold on, and I will just decrease my t. Not holding. This is more becoming like a step input. At the end, it will become a step input for tau equal to 0. This is what we observed. Okay. Okay, moving on. This was just how do you increase or decrease a variable and run the entire code. You don't have to just manually change the t and run each time. You just have to increase or decrease the value. वो मैं यहाँ पे कर रहा था. ठीक है? Let me just go back to the t that we used. मैंने लिया था 0.4, I guess. और k2 मैंने लिया था 0.74, I guess. Okay. So this is the LSIM command, or you can use simply the step command. Okay, let me just go to second order system quickly. Second order system, you can define a number of ways. Either you just define zeta omega, then write the transfer function, or you're having this, आपके पास already है ना एक system, system 1 and system 2, these two. If I do the product of those two, again I'll be having a second order system because these are both first order systems. If I do the product, I will get a second order system. And that's what I will do. I will create a system by the name system 3. And that will be system 2 times system 2. Okay. मैंने एक system बना लिया, system 2, which is already this form, and again a system 2. So the product of those will be second order system. Let me run this line only. See, this is your second order system, product of those two, and I'm having this K2 दोनों में same रहेगा, ठीक है? And let's simulate this system 3 now using the same LSIM command. I want to see it periodically, how it behaves periodically. Y, T. Just run this. Again, there is no function by the name system3, system_3. See, this is the second order system for again that step जो हमने स्क्वायर वेव बनाई थी ना, ये स्क्वायर वेव. बट इफ यू सी आप यहाँ पे कोई पीक्स नहीं ऑब्जर्व कर रहे हो, जैसे हमने देखा था सेकंड ऑर्डर सिस्टम्स में. व्हाट इज द रीजन? व्हाई एम आई नॉट सीइंग सम पीक्स हियर? व्हाट कैन बी द रीजन? कैन एनीवन टेल मी यहाँ पे पीक्स क्यों नहीं आ रहे हैं? सेकंड ऑर्डर सिस्टम्स में तो हम देखते हैं ना ऑसिलेशंस. देयर आर नो ऑसिलेशंस. It's as if we have simulated the first order system. What can be the reason? Anyone? Any guess? कोई भी आप guess ले लो कि इसमें हम oscillations क्यों नहीं देख पा रहे हैं? Anyone? Nasir, are you connected? Sana?
Yes, sir.
Can you tell me यहाँ पे oscillations क्यों नहीं expected है? क्योंकि हम तो ये simulate कर रहे हैं ना second order system, but I'm not seeing any oscillations here. Any reason that you can think of?
So क्योंकि ये टाइम डोमेन में है एंड मतलब oscillations हम शायद ऑब्जर्व नहीं कर.
See, I'm simulating this system ना, I'm simulating second order system. So expected जो है second order system जो है उसमें oscillations रहती है.
Yes, sir.
But here you don't see an oscillation. जैसे ऑसिलोस्कोप पे देखा था वैसा तो नहीं है. It's just like a first order system. The first obvious reason is the damping is high. इसमें oscillation इसलिए नहीं है.
ये बहुत जल्दी ही सेटल हो रहा है, इसलिए हमें नहीं दिख रहा है.
Exactly. Oscillation इसलिए नहीं दिख रही है क्योंकि transients are quickly dying. And the reason is the K, this K. The K is very small. क्योंकि जो transfer function है इसमें जो है K हमने product किया ना of system 2 and system 2. See if I just decrease this K. See, I will show you. इसमें मैं जो K2 है involved, I will just increase this K. Let me just increase this to 5 and run this. Wait, again there is some error. It says plots must be of same type and size to be superimposed, and this is in line 20, which is this. एक काम करते हैं, जो पुरानी plots हैं इनको comment out करके रखते हैं. This is the first plot. This is the second. इसको भी बंद करते हैं, इसको भी बंद करते हैं. Hold down command भी बंद करते हैं. This is also a plot. Let's simulating system 2 को रहने दो. System 3 is here. And system 3 y, t. Just run this. This is K2 is 5. Again, I'm not seeing any oscillation. The reason is K2 is 5 and T is what? T कितना लिया हुआ है? T is 0.4. Let me just change this T also. Let me just change this. See, I've just grabbed this here. इसको मैं यहाँ पे ले रहा हूँ. और जो system 2 है, this one, I'm also moving it here. Okay. And K1 की कोई जरूरत नहीं है. K2 is 5, T is 0.4, and I'm just producing system 2 with system 2. And yeah, there's one more thing. ये जो हम simulate कर रहे हैं, there's one question that you should have asked. कि हम जो simulate कर रहे हैं, whether it's an open loop or closed loop. It's basically an open loop. When I simulate this system into system, that's a second order system. That's an open loop, and you cannot expect कि इसमें जो है oscillation आ सकती है क्योंकि कोई feedback नहीं है. So in order to give a feedback, see, I will use again the command feedback of this whole thing, or Let me write this. Feedback of system 3 with a unity. Okay, and इसको मैं system 3 CL means closed loop, मैं closed loop से represent कर रहा हूँ, and this. Now for run this C. ऐसा ही आपने प्लॉट देखा था ना नॉसॉस को.
सर इसका मतलब ये ऑसिलेशंस हमें फीडबैक की मतलब जब हमने क्लोज लूप किया था तभी
only,
देखी.
not only because of the feedback, two reasons. एक तो गेम जो हमने सेट किया था that was different, and the reason was also of the feedback. Open loop system if you simulate, तो हमने देखो, I will show you both the transfer functions. इसको यहाँ पे लेते हैं. This is the system 3 without any feedback, and this is the closed loop feedback. It will be different. इसमें जो denominator polynomial है, that will be different. इसमें जो है देखो, this term corresponds to what? This term होती है इस omega m square, isn't it? यहाँ पे omega m square की term में 1 है, और यहाँ पे omega m square की term में 26 है. And you know omega m square is basically what? It's the natural frequency of oscillation. So इन दोनों systems में different होगा. इसमें थोड़ा ज़्यादा होगा, तो इसमें almost ऐसा value है कि होगा ही नहीं. That's why जब हमने ये simulate किया था, इसमें कोई oscillation था नहीं. और इसमें you can see some oscillations corresponding to this value 26, and which is here. तो ये जो मैंने plot दिखाया, this is for some periodic square wave. अगर आप simply एक step लोगे, instead of LSIM, if you simply do a step of system 3 enclosed and run this, it will show you a prototype second order system for just a positive half of the signal. And यहाँ पे MATLAB में जब आप plot करते हो step function or step command, you can calculate various things. Oscilloscope में जब हम measure किया करते थे peak time, rise time, overshoot, steady state, used to measure it from the grids or the values जो oscilloscope पे रहते थे. यहाँ पे in MATLAB you can just right click on the figure, go to characteristics, and you can just see any one of them. You can see, let's suppose, settling time. It has a settling time of 1.55 seconds. Similarly, if I just open rise time, if I open steady state, if I open everything, see, this is your rise time, 90 milliseconds. This is your peak time, 25.25 seconds. This is your settling time, and this is your final value, which means the steady state value. The steady state value is 0.9, which means इसमें कुछ error है, because we're comparing it with 1. As compared with 1, it has some little bit of 4-5% of error. Okay? This is how you simulate first order system for any periodic input or a step input, or you simulate a second order system. And you can simulate both in open loop and closed loop. For closed loop, you just have to type this command feedback to create another transfer function. Then do the step of that. So this is how you simulate it and how you can check these values. Okay. Now, अभी तक तो जो हमने किया, that was some basics. We will do a last, what you call, एक last script बनाते हैं. One more script. And यहाँ पे थोड़ा हम आएंगे on the control itself. अभी तक हमने कोई control नहीं किया. We didn't provide any control to thing. अभी बस हम system को analyze कर रहे हैं. We are analyzing transfer functions. We are analyzing state space models. We analyzed first order and second order. अभी तक design में नहीं आए. क्योंकि जो last experiment जो था, that was most important experiment. It was design a controller to modify the behavior of something. Let's suppose यहाँ पर हम एक final script ले लेते हैं, and what I want is I want to design something. और जब मैं last time use किया था, that was lead and lag. आपने वो वीडियो देख लिया है? Has every one of you watched the video for design or not? See, हमने जो last time वीडियो experiment लिया था, उसमें हमने we took some design criteria in mind. We took the design criteria of, if you remember, 5% steady state and 40 degrees of phase margin. See, these things will make sense only when you know these things. और ये चीजें मैंने revise कराई थी in lab. So if you haven't watched it, so I suggest कि जब ये वीडियो मैं अपलोड करूंगा, just first watch the video for the design, then you see the script, क्योंकि तब आपको समझ में आएगा कि चीजें क्या हो रही है. And I will save this by the name. Let's close design on desktop. से यहाँ पे हम 5% स्टेडी स्टेट एरर और 40 डिग्री फेज मार्जिन के लिए डिजाइन करेंगे लीड लैग सिस्टम. तो जो हमारी ट्रांसफर फंक्शन है, इसके लिए हमें कर रहे हैं ट्रांसफर फंक्शन आपने ऑलरेडी एक एक्सपेरिमेंट में ओपन की हुई है. लेट मी जस्ट ग्रैब दिस मैनुअल. ये जो था हमारा एक्सपेरिमेंट डिजाइनिंग, इसमें जो हमने ट्रांसफर फंक्शन ओपन की थी, which was very similar to जो आपने body plot से obtain की थी, very similar. The value is this 4.44 upon 1 plus. This is second order system type 0. तो इसके लिए हम डिजाइन कर रहे थे. So let me just write this transfer function first in MATLAB. Going to MATLAB again. I'm just writing this transfer function. So again I will just first clear everything, CLC, and I will just close everything. Okay. And I will create the transfer function by the name system. That's 4.466 upon 1 plus 0.001768 into S. You have to take care of every notation.
सर हमें ये नहीं आया था, हमें आया था 1 plus 0.0029 S, तो आप वही लीजिए.
ठीक है, 0.0029
और ऊपर 4.45 था, so that
that's very good.
वेरीफाई हो जाएगा ना.
It's almost same. इसमें फर्क नहीं आएगा. ठीक है, हम वही वैल्यू ले लेते हैं. 4.45 divided by 0.0029 S whole square. ठीक है, ये ट्रांसफर फंक्शन हमें सेव कर लेते हैं. And what I want before you go to design is to know the system. Before you design a system, the first step is to analyze the system at hand. एक फिगर बनाता हूं मैं, ब्लैंक फिगर, उसमें विल प्लॉट द बॉडी. अभी मैंने दिखाया था हमने बॉडी कैसे ले लेते हैं. सिंपली द बॉडी कमांड. सी दिस इज द, should just take the grid. हाँ, this is the open loop body diagram of this, much similar to जो हमने experimentally obtain किया था. This one. ठीक है, just forget this and focus on this now. हाँ, तो ये आपको ओपन लूप बोर्ड है फॉर दिस ट्रांसफर फंक्शन जो आपने एक्सपेरिमेंटली ऑब्टेन किया था. यहां से भी यू कैन गो टू कैरेक्टरिस्टिक्स एंड यू कैन सी द स्टेबिलिटी मार्जिन्स. सी MATLAB will show you the phase margin. कितना फेज मार्जिन है सिस्टम में ऑलरेडी? इट्स 56 डिग्रीज. ठीक है, एंड देयर इज नो गेन मार्जिन, एंड आई हैव टोल्ड यू इन द लैब गेन मार्जिन क्यों नहीं है. एंड यू कैन आल्सो draw the peak response. In body plot, peak response is the response at 0 frequency, which is 13 dBs. So this curve cuts the y-axis at 13 dBs. So 13 dB का gain आपके पास, and you're having a phase margin of 56. अच्छा, if I ask you what's the steady state error for the system? Open loop system without any control, what is the steady state error? See, steady state error you cannot quantify from body plot. You can, although मैंने दिखाया था कि at low frequencies steady state error define किया जाता है for some input, and when I mean by steady state error, I by default mean step input. तो step input पे आप इसको close करो and output आएगा उसका steady state error में पूछ रहा हूँ. In other words, what I'm saying is do the step of the feedback system. I'm asking you this. ये मैंने फीडबैक ले लिया फॉर अ स्टेप इनपुट यूनिटी के साथ. You go to steady state. This is your value. Final value is 0.817, isn't it? तो उसमें steady state error कितना होगा? Steady state error will be 1 minus 0.87 because final value has to be 1. Why? Because I'm providing a step input, unit step input. तो देखो 1 से काफी दूर है ना, 1 से काफी दूर है. But in my design, I want the steady state error to go to 5%. 5% error कितना हुआ? 5% error होगा if had it been final value almost 0.95, isn't it? 0.95 पे आपको 5% मिलेगा. So this has to go up. And another design is I want my phase margin to be 40 or more. क्योंकि phase margin system में जितना होगा उतना अच्छा है. So I want it at least to be 40. 40 से कम नहीं होना चाहिए. This is my design criteria. And to begin with steady state error इसमें system में या यहाँ पे मैं लिख लेता हूँ. जो system है, system has 56 the phase margin and final value of how much कितना वैल्यू था 0.817. तो ये जो चीजें हैं इनको हमें मॉडिफाई करना है. ये सिस्टम की इनहेरेंट प्रॉपर्टीज है. क्लोज दिस. नाउ आई विल स्टार्ट माय डिजाइन फर्स्ट. लेट मी जस्ट for your ESS to be 5%. See, what I have to do, I have to जो आपको ओपन टू बोल रहे हैं, and I explained this in lab specifically कि how do you जो स्टेप होता है, सॉरी जो आपका डिजाइन रहता है उसके दो कंपोनेंट्स रहते हैं. The first component is to correct this one, steady state error, and second component is to correct the phase margin. Now we will divide the design into two parts. First part maybe we will just correct the steady state value, and in the second part when we will switch to phase margin, we should not disturb the design for steady state value. That thing has to be kept in mind. And first I am going for steady state. I will not care for phase margin right now. I will just improve the steady state to 5%. ये कैसे करेंगे? जो आपको ओपन लूप बोल रहे हैं उसका मैग्नीट्यूड you have to increase by 19 by 4.45. Now how come this value comes? This 19 is basically, if you remember, हमने जो for a step input we are talking. So steady state error for a step input of a type 0 system is 1 upon 1 plus kp, if you remember. I don't know if I have this table here. Somewhere वो table था. This one. For a type 0 system and for a step input, you are having the steady state error as 1 upon 1 plus k. And this thing I'm equating to 5. Sorry, 0.05. Because I have to make this thing 5%. This is my design. So when I equate this thing to 0.05, the value of k that I will need is 19 to solve this. Ab 19 to mera value aa gaya. How much gain I have to increase? I have to increase this gain. I will not have to increase 19. I have to increase a fraction 19 upon the already gain present in the system, which is 4.45. And from here I will get a constant. Let's suppose this is 5. I have to increase the gain of an open loop body by 5. And in dBs, in the body loop, we don't use gain as very simple constants. We use in dBs. In dBs, that's around 14 dBs. Okay. 20 log of 5 is no, this is not correct. There is some wrong. Something is wrong there. We have to, क्योंकि हमने जब ये calculations की थी, जब हम calculations कर रहे थे, the lab, if you remember, no, this one. Let me show you. Yeah, this one. See, 19 upon 4.44, that was 5. And you increase that by 20 log of 5. But this may not be natural log. I suppose this is not natural log. This comes to be around 14 dBs. Okay? So ये करने से क्या होगा? आपका steady state error will go to 5%. Let's see. Let me make another system with C. C means compensated. Okay? So what I have to do, I have to multiply 5 with the original system. In time domain, I'm just multiplying it 5. ठीक है, तो if you see the system is, I run this is the modified system. इसमें बस gain 5 times हुआ use, otherwise everything is same. ठीक है, so if I do go to the body plot now, if I do the body of both the original system and the compensated system, see, I have done nothing. I just increased the gain from it was earlier 13. Let's see, from 13 dBs to 27 dBs, which means I have increased 14 dBs in the system. Phase के plot में कोई change नहीं आएगी, and magnitude I have just increased to 14. And in doing so, I'm suggesting that I have improved the steady state error. Now, have I improved my steady state error? I can verify. I can go again to the step of the feedback command of the new system. The new system is system_c, comma 1. See the the steady state value 0.95, which means 5% error. If I plot side by side, if I use the command hold on, and if I plot the previous system also, उसमें पुराना system ले लेते हैं, C नहीं है उसमें. See, this was my older system, जिसमें 0.817 था final value. Now I have changed it to 0.957, which means I essentially improved the steady state value. But still we are having 5% error. See, 1 से ये 5% का दूरी है इसमें. That was my design. My design was to make it 5% or less. Okay, that's step 1. Now step 2 of the design is to make the phase margin equal to 40. If you see from the body plot, my phase margin initially was 56, if you remember, है ना? लेकिन मैंने चूंकि gain को बढ़ा दिया, I have increased the gain. This orange is basically the compensated, and the blue is uncompensated. ठीक है? तो orange is the compensated one. So I've increased the magnitude. So this gain crossover frequency, which is here somewhere. See if we just see. This was the earlier gain crossover frequency, 640 radian per second. 640 radian per second is omega. Okay, and I have shifted that to here. I have shifted that to here. Now, क्योंकि magnitude ऊपर गया, तो gain crossover frequency has shifted from this point to this point, which has dropped my phase margin. My phase margin earlier was 56. Now my phase margin has dropped 24. This is because of the addition of gain in the system. So my phase margin has dropped to 24, but I want it to be more than 40. So अब हम एक controller design करेंगे which will bring it up to 40 or more. But it should not disturb the steady state value, which is the 5% steady state value. इसके लिए in the lab we saw 2 techniques. The first technique we saw was for designing a what we call lag system, and another we saw as lead. There are 2 options to do that. ठीक है? So मैंने जो design philosophy है उसको मैंने explain किया था in detail in the lab कि how do you design a lag system to compensate for the phase margin, and how you design a lead system to compensate again for the. These are 2 different approaches to do the same thing. Very quickly I will just write the transfer function or the value. See, for a lag हमारे पास जो आ रहा था values, these were the values that we get, और जो lag की transfer function रहती है, that was given here. This is the transfer function for the lag. See, very quickly we'll just write this transfer function. For lag, let me just write the transfer function this. So I have to store the t and beta. So for lag, I will store my beta. And if you go back to the notes or the lecture, the values that we derived in the lab were these. Okay. And the lag के लिए जो हम transfer function लिखेंगे, that is t into s plus 1 then divided by beta into E into S plus 1. I have written basically this transfer function for the lag. Okay, this is a transfer function of the lag with constants beta and t. How we obtain this beta and t? This comes from the design philosophy. You can again refer back to the video where we derived these values. But यहाँ पे मैं बस समझा रहा हूँ कि how you can use MATLAB to do these kind of things. यहाँ पे बस मैं पहले verification दिखाऊंगा, then we will just see how you use MATLAB for those things. I'm just using the previous system, and I will just multiply my lag now. See, this is the compensated system for 5% steady state error, and this is the modified now. इसमें हम multiply करेंगे with the lag transfer function, which is this. I'm multiplying these two transfer functions, system underscore C and the lag. See, यहाँ पे forget about this. See this. Characteristics or stability margins. वेट यहाँ पे दो फिगर्स आ गई. ये वाली फिगर जो है I don't want this body plot and I don't want this also. Just commenting out various things. हाँ. 24, 39.1. ये जो डिफरेंस आ रही है, it's not 40. ये जो डिफरेंस आ रही है, it's because कि हमने ट्रांसफर फंक्शन जो ली थी, जैसे सना ने कहा था कि you just change this. हमने क्लास में जो लिया था, it was this. But this manual में जो है, it was a little bit slight. एक difference थी on the denominator. The transfer function was 176, and here it's 0.0029. And for the lag, I'm taking the value suggested by the manual. So let me just quickly write this. यहाँ पे मैं इसको. But design philosophy will be the same. Okay. See if I run this now. Run this now. This passes my 40% test. So if by the effect of lag, what I have done is basically I've improved my phase margin from 24 to 40, and at the same time I have not disturbed my steady state error. See, magnitude mein jo steady state error, that's again the same. So I'm expecting if I take the feedback and I take the step response, the steady state error still will be 5%. One other approach was to go for lead. Lead ke liye, see, this was the transfer function of the lead. Transfer function of the lead is somewhere here. Class. See, if I take the transfer function, I have to define first this alpha and t. So alpha is 0.39 and t, I will the TA. If I remember 1648 or something value that we were getting. And the transfer function of lead is defined in a similar fashion. Alpha into S into TA plus 1 over alpha into S into TA plus 1. See, this is the transfer function of the lead. And again, you have to do the same thing. Plot the body plot of everything that you have till now. Body plot of the compensated system, 5%. Body plot of lag first, lag with the system, and body plot of lead now with the system. C. Just commenting this figure. यहाँ पे मैं सब कुछ plot कर रहा हूँ. I'm plotting the 5% error, the lag compensation, and the lead compensation. Okay, and let me just quickly run the legend. ताकि आपको this is a steady state 5%. This is lag, and this will be your lead. मैं बस comments डाल रहा हूँ ताकि आपको visualize हो जाए. See, if you go to characteristics now, The blue one is uncompensated, जिसमें कि 24% phase margin है because of addition of magnitude. The lead, focus on the lag first. Lag is the red one. 41, again it's satisfying the design, and lead is orange, which is also 43 something. So it's again satisfying my 40% margin. ठीक है, लेकिन यहाँ पे डिफरेंस मैंने क्लास में समझाया था कि ये this was my earlier phase gain crossover frequency. Effect of lead was to shift this to right here. This point was shifted to right, but for lag, this point was shifted to left. So this is the action. Either you can go to left or you can go to right, and you have to account for the body plots of lead and lag to account for this 5% steady state error. Yeah. जो lead है, if you see this orange one has increased the phase margin of this blue curve. इस blue curve के ऊपर एक additional phase add हो गया, और जो lag था, lag ने basically attenuate किया था magnitude, if you remember, से कहीं किसी frequency पे attenuate किया था, वो हमने derive की थी, और उसी value पे magnitude भी drop हुआ था. उसकी वजह से क्या हुआ, उसकी वजह से phase crossover gain crossover frequency has moved to left, और उसी point पे मेरा 40 something phase margin आया था. This was the design philosophy, and I just validated the design here. In MATLAB, if you don't know the design, let's say आपको पता नहीं है constants कहाँ से आए, transfer function कहाँ से आई, so I have also showed you what you can do is you can use MATLAB to design things. I will just take 3 minutes to just show you how you can use MATLAB to design. See, if I write design via MATLAB, we have the system SYS, isn't it? Yeah, the command window use कर लेता हूँ. So
ऐसा पे ईमेल नॉर्मल मार्क कर देंगे कभी छुट्टी है आइडिया से लेकिन तो कोई पता लगना.
अच्छा ये पेज जो उसमें बस बेसिक का पैनल सर्किट्स वो भेजा आपने, मैं फिर ऐड करके भेजता हूँ.
वो लिस्ट बनाया तुमने स्पेशल?
हाँ, वो भी मैंने बनाया, और वो आंसर ओन मार्क शीट बनाया.
मेल बनाओ कि मैसेज कर
आपको मेल करता हूँ,
फिर देखेंगे अगर पढ़ी जरूरत तो फिर मैं दूंगा.
ठीक है. So in MATLAB, you're having this CISO tool. It's case sensitive. You have to use small CISO. Very quickly, I will show you. You can just skip further details up online. Very quickly, I will show you. This is an app in MATLAB by the name Control System Designer. Okay, this opens when you type CISO tool of a transfer function. See, this is a very intuitive app. On the left, you can see the body plot. Open to body plot. And on the right, you are seeing a step response, and on the top, you are seeing a root locus. ठीक है, 3 plots आपको simultaneously दिख रहे हैं यहाँ पे single system. इसमें कोई हमने compensation add नहीं की है. And this app is used for designing things. यहाँ पे what I will do first, I will just mark some things. I will just write design requirement. I will add a new requirement, and my requirement is that I should have a gain को भूल जाओ 40. I should have at least 40% gain margin. Okay, sorry, phase margin. ये मेरा एक डिजाइन है, और 5% steady state error. तो ये 2 steps हमने अचीव किया था. पहले स्टेप में what we did is if we go to body plot, यहाँ पे आप characteristics में you can see to improve the steady state value from 0.81 to 9.5, you just have to increase this open loop body. See, I will just drag this magnitude up, and simultaneously you can see the effect on step response and root locus. See, as I'm moving the gain up, my step response is improving. लेकिन इसमें oscillations भी बढ़ रही है, and I have to stop somewhere. See, if I stop around here, see my steady state criteria is met now. It's 9.6. It has improved, and this is by the way closed loop step response. तो यही हमने किया था. हमने 14 dB का magnitude increase करके steady state error को improve किया था. Now the second is phase margin. Phase margin को improve करने के लिए either go for lead or go for lag. वही हम यहाँ पे करेंगे. I will show you one. I will just add here. You're having this right click here, add, and you're having a bunch of tools, and one among them I will use. Let's suppose I use lag. ठीक है, I will select lag, and then this cursor has turned to this pointer thing, and I can add pole zeros now. Let's suppose I add pole zeros here. See, in the root locus has modified. अभी तक root locus जो था having 2 poles only, लेकिन अब आपने एक पोल और एक जीरो ऐड कर दिया, and उसकी इफेक्ट से ये भी चेंज हो गया और ओपन टू बॉडी भी चेंज हो गया. Now depending upon the location of the poles, you can tweak the response. See, if I move this pole left, और यहाँ पर आप ट्रैक करते जाओ, gain phase margin is how much? 24, है ना? Just track this phase margin as I'm moving this pole. See, it's improving. So there will be a particular position of pole zeros जहां पे मेरा phase margin criteria met हो गया. See, 41, isn't it? So I have 5% steady state error as well as 41 phase margin. Now this is my tweaked controller, and I want to save it finally. You can go to again control system, and you can see edit compensator. Here is your compensator. It has added a gain of 5 जब हमने derive भी किया था, and these are the locations of poles and zeros, and it has stored by the name of lag. If I store this, export, here is the export option. You go to export, and there are a bunch of values. ये basically आते हैं from the structure. I will just export this C. C is basically the compensator. I will show you. This is the architecture. Here it's C, this C. You can also export this F, G, H, but I'm exporting the compensator, which is the C. So it has exported the C value. Here. ये है आपका lag compensator. And if I use this lag in product with my system, and I do the feedback of the whole thing. I will do the feedback of whole thing, and I do the step of the final thing. It should be expected कि ये वैसा ही होगा जैसा कि होना चाहिए. See. Settling time नहीं. Steady state. Wait, there is something off. Feedback of lag. No, I don't have to take feedback of lag. I have stored the variable as C. But C I have stored, not lag. Characteristic, steady state, it's satisfying my 5% rule. And if I have to track the phase margin, what I will do? Phase margin I cannot get from step response. Phase margin I can get from body. So that is body plot. Or just write the body simply. Body of your C times your original system. There should be a plot. ये नहीं, यहाँ पे. This one. We are satisfying 41. So we are satisfied the steady state well, and as well as the phase margin. Similarly, you can do for lead. मैंने एक lag के example दिखाया. Similarly, you can use this app to obtain a lead, and you're having a bunch of other things also. So this is how you use MATLAB for design. If you don't know the equations, if you don't know the philosophy of design, you can use MATLAB as a tool for designing or controlling the behavior of a system to any set value. Okay. So by this, I conclude this session, this MATLAB session, and I hope I have this. By this hour, I have just introduced MATLAB as a tool for control systems course. और मैंने आपको थोड़ा सा आइडिया दिया about the state space modeling. मैंने आपको कुछ चीजें दिखाई जो आपने डिस्कस की हैं in the class about controllability and observability and so on. So आपका एग्जाम जो है it will be on 1st December. आप just revise करो everything that we have taught in the video, और ये जो आज का वीडियो है इसको भी देखो अच्छे से. And if you have any question or query, you can just ask me in the WhatsApp or mail me. आप मुझे कर सकते हो, शेयर भी कर सकते हो. And thank you. So all the best for our exams. And I'm just stopping the meeting. Okay.
Excuse me, sir.
Yeah.
सर हमने लैब में जब लीड लैग का किया था ना, सो उसके बाद हमने वो सर्किट्स में वो कैपेसिटर और रेजिस्टेंस किया था. लीड लैग हमने वो सर्किट्स हमें पता थी लीड लैग का क्या होता है. फिर हमने ऑसिलोस्कोप में वो कंपोनेंट्स ऐड किए, तब जाके हम वो ऑब्टेन कर पाए. सो मैटलैब में यहाँ पे हम मतलब वैसे नहीं करते हैं, लाइक मतलब
MATLAB is basically to simulate things. वहाँ पे आपने जो लीड लैग ट्रांसफर फंक्शन कैसे रियलाइज की थी, practically you transfer function थी, you realized that using a circuit, this circuit, है ना, आपने realize किया था using a circuit physically. But in MATLAB, simulation wise, you can simulate this circuit response using a transfer function. वही हमने किया, हमने transfer function के थ्रू उसको simulate किया. But practically, the transfer function can be simulated using an RLC component or RC components. वो हमने physically verify किया. यहाँ पे हमने इसको simulate किया बस. यहाँ पे you don't need to find a circuit in this model. Okay? और कोई doubt है? Sana, any doubt?
No, sir. No, sir.
Okay. Okay. Thank you so much.